Well, welcome to the second session of the Intermediate Lisp course. Today we're going to finish up the slides that we didn't do from session 1 last time, and then get on and discuss the Common Lisp Object System, or CLOS. The first thing we're going to do, though, is just briefly go over the homework, and I'll go through these as quickly as possible. If you have any questions about the homework, just send email to training@franz.com, and I will try to answer your questions. First of all, there were just define a number of simple functions. If you took the elementary course, all this material was covered there. Here, the first one is a simple function that simply does something. What it does is print hello, hello out there. The second one, this has an optional argument where you can specify a stream, and the default value is T, and the symbol T has a special meaning when it's given to a output function saying send the output to standard output, which is a built-in stream in Lisp, typically the same as the terminal. The second one, instead of using an optional argument, it uses a keyword argument. And then the third simple function here is the sum function. It has an and rest argument, and it binds a local variable result to 0 and then runs through all the arguments, which, because it's an and rest argument, is bundled up into a list, and adds each argument to the value of result. So at the end, result is the sum of all the arguments, and then you return that. Here is a setf function, and we first define a function called myThird of mylist, and it takes nth of 2 of mylist. Remember, list is 0 index, so nth of 2 is the third element of the list. And then we want to define a setf function on our function myThird. And so it's got to take 2 values, the new value and the argument list. And we do a little bit of checking to make sure that the argument list is really a list and that it really has 3 elements. Once all those things are true, we replace the third element, and you do that. Well, there are a whole bunch of ways to do it, but this one is with the operator RPLACA, pronounced replaca, of the cooter of list. Once we've done that, replaca is a function which modifies its argument. It doesn't destroy its argument. It just modifies it in a predictable way. The list is now modified, and it's returned. Here we have an example of using hash tables, and we're looking at a function which simply squares its argument. And so if you want to write such a function, you would, here it is. The function expensive takes 1 argument, squares it. But suppose that the actual calculation of the function is expensive, meaning it takes a lot of computer resources. You might want to save values that you've already calculated and use those already calculated values when they're available. Now, of course, squaring a number is not truly a computer resource-intensive operation, but you have to imagine this is standing in for something which really does take a lot of computer time. So we create a hash table, and then we define a function frugal. And we are storing things in the hash table indexed by the argument x, with the key in the hash table being the argument x. So first of all, we look at the value of result, and that is the result of looking in the hash table and seeing whether x appears as a key there. When it doesn't, then we calculate the value that should be returned, square of x in this time, and then we store the value in the hash table, and then we return it. Now, remember, we had a discussion last time that get hash, the first return value can be nil because the value associated with the key is nil, and there's actually a second return value which you can examine to see whether the key was in the hash table but had a value nil or wasn't in the hash table at all. However, in this case, that's not necessary because we know these things are numbers. They have to be numbers. That's the only thing that's valid to pass to the function star. And therefore, we know if the value's there, it's going to be a number. It's not going to be nil. So if we get nil back, we know that the key doesn't appear in the hash table. Here's a mapping function to sum things up. We had an earlier function for summing things up. And so here we are, this is using the map function as a summer. We start out with the result, local variable result being 0. We call map C, which is one of the mapping functions, and maps, I think maps the car of the argument list. We define a function which is takes a single argument and sets the value of result to be result plus x. And so that's the function is defined from here to here, and the second argument to map C is the argument list that was passed in, and then we return the value of result. Notice that the result local variable appears in the definition of lambda, and that's permitted because it's within the scope of this let statement. So you can have local functions that depend on variables that are defined outside of them. We don't need another let statement in there of any kind. So this is just another way to sum up functions. There are a whole bunch of ways to do that. Here we're looking at multiple value. Truncate returns multiple values. And here's the multiple value bind form. Now, I was trying to type one of these in from memory last time, and I got it wrong because I put an extra set of parentheses around. I put an extra opening parenthesis there and an extra closing parenthesis here. But if you think about it, this, as written without those additional parentheses, is not ambiguous. The first argument is a list of symbols, which are going to be the local variables. The second argument is the form you're going to evaluate to get the multiple values, in this case, truncate and num and div. We're interested only in the second value returned by truncate, that is result. And so within this multiple value bind form, we put a declaration saying we're going to ignore the variable x. And so when you compile this, the compiler is going to see, oh, he's not using the variable x. And notice the variable x doesn't appear after its value is bound. The function's not using the variable x, and the compiler would print out a warning saying variable x not used, because the compiler generally tells you when it thinks that, well, perhaps you've done something wrong. Its view is, why did you create the binding for the variable x if you weren't going to use it? The answer in this case is we were forced to do so because we're trying to capture two values. We're trying to get the second value of a function that returns multiple values, so we had to have something that was capturing the first value. We were just uninterested in it. That's why we told it to ignore it. Certainly when you have a let form, it's somewhat more surprising if you give a local variable a value and then don't use it, and you would also get a warning there. However, sometimes when you're programming a complicated function, you often do a let binding, and you create a lot of variables because you think you might use them, but then you get down into the body and you discover that several of them you don't end up using. then you'll get the warning, and you can either go back and recode and get rid of those things, or if you think, well, I might need them if I modify the function later, you just put in a declaration to ignore them, or there's another declaration called ignorable, I-G-N-O-R-A-B-L-E, and that just tells the compiler this may be used, it may not be used, don't say anything about it. But if you have an ignore and then you actually use the variable, you get the other warning which says, you told me to ignore this, but here you are using it. If you have an ignorable declaration, then the compiler just won't whinge about it at all. Here's some more hash tables. Using a hash table, write the following. And what you're trying to do is count the number of the various symbols that appear in here. 1, 2, 3, 4, yeah. So all the symbols. We're not counting the number of A's that appear anywhere. We're counting the number of times the symbol A. So it doesn't get counted for this CA here. This is a somewhat more complicated thing. First of all, here is the function that will print the results. If we have a hash table which has associated every symbol with its number of occurrences, let's see, what am I saying that right? If we have a hash table, what's the hash table going to do? So we're doing a map hash. We're pushing, yes. So this one is accessing the hash table. The hash table has to associate a symbol with its number of occurrences. We assume the hash table already exists. This function here is simply binding everything up in a list that looks like this. So this will work when we have such a hash table. We don't have it yet. Now here we have a function which fills the hash table. It goes through everything, and it is, here we're doing a multiple value bind to see whether things are already in the hash table, and if they are in the hash table, we increment their value, associated value by 1. If they're not in the hash table, we stick them in the hash table with the value 1. And let's see, so here's the function which binds everything together. We create a hash table, we fill it, and then we do the verify. We only got a little bit into macros last time, but there were some questions on macros. I'm not going to go over this. This is too much. If you have questions about this, but basically we are defining a macro which takes a tag and content and which formats the thing into an HTML version of less than tag greater than, then the content, then less than slash tag greater than. And that's basically what we're doing here. We've defined an output tag that is a function which takes a tag name and determines whether it's an initial tag which will not have a slash or a final tag which will. And here's a macro for doing that. And then we've got another macro which which is wrapped around all of the content and body we're going to have. And so if you put those things together, you'll get something that will produce HTML. That's the point of it. Try that example if you haven't done it yet. There is already a macro in Lisp called rotate F, and what rotate F does is that you have several symbols which you've listed in order, and you want to rotate the values. So the value of the first one becomes the value of the second one, the value of the second one becomes the value of the third one, the value of the last one becomes the value of the first one. And notice that what we're doing is we're actually we're only rotating symbols for 2 symbols here rather than, well, here rather than huge number, but here we're, so we bind local variables val1 and val2 to be the value of the two arguments, and then we just set the two symbol arguments to the two values in reverse order. Here is our version of MyDefun, and what we're doing is we're setting up the symbol function to the function object. Here's an anonymous function object, which takes the arg list and the body. This is a pretty abbreviated version of defun because it's well, if you remember, we macro expanded defun, and in the system it does a whole bunch of things which you usually want it to do, but this will actually set the symbol function of a function name to the definition that you've provided. And here we're doing our version of my type case already, again, a list macro, and this is a little bit more complicated because type case like cond and similar like cond and case are made up of clauses. So we, first of all, have a function which creates the clause, and then we have a, let's see, we had make clause one, right? Here's make clauses that creates the whole list of clauses, and here we, by the time we've set up all the machinery, the actual my type case macro is relatively simple. Now, the problem, here you see one of the problems with macros, which is, you're sitting there and you're trying to read that, and you got to go back to where all these definitions are. Macros are very useful, but their source code isn't the easiest thing to read, and so you just have to remember that when you're doing it. So those were just a quick overview of the homework, and let's go to, this is from day one. This was slide 86 where we ended up last time, and we're just going to proceed from here. So we're just, well, the previous slides were a number of macro definitions, and here are just a couple more. Here, remember, the purpose of a macro is to take a form with the macro name and then arguments and convert it into another form which will then be evaluated. So here we have the atomic pop form, and what atomic means in this case is that this will run without interrupts. And without interrupts means that if you send in a signal, for example, hitting the break key, it will ignore it until it's completed. In a multiprocessing environment like we have in our list, the thing is that you don't want certain things changed, and if it was able to go to a different thread, maybe the values of list would be changed and it would get confused in this point. So without interrupt says we're going to complete this operation making sure that nothing else is happening while we're doing it. So all this macro is doing is it's adding a call to without interrupts. Without interrupts, by the way, maybe it's in the ACL package. You have to figure out which package it's in and make sure that you have to package qualify it correctly. And then we just use the standard list function pop, list macro, standard list macro pop, and apply it to the list. Pop, remember, takes the first element off the list and modifies the list to not contain the first element. Here is the same thing, except we're doing it with push. And when you have push, you need an item in a list. And so we call the predefined list macro push there. Here we have a macro called while, and it has a test and then a body. Now, here we go in and we use the do operator, remember the do operator, first of all, starts out with a number of initialization forms. We don't have any initialization forms, so this list is empty. And then it has a test form, and when that test form is true, what do we want to do? Well, while means while the test form is true, we keep going. So we want to stop when the test form is false, and that's what not applied to a form. If the form is nil, not becomes of the form becomes true. If the form is anything that's not nil, not of the form becomes nil. So this will be true when the test form returns nil. And then here's the body. That's where the body goes in call to do. So what this macro does is that it has a test form, and it starts evaluating the body and keeps evaluating it again and again and again until the test form returns true. So here we're saying we start with I equals 0, and we're saying while I is less than 10, we print I, and we then increment I by 2. So let's see if we can. I'm just going to go illustrate this because this is kind of a good example. Let's see if we can do this. There's the. By the way, here I was doing the get hash to show you the multiple value bind correctly without the extra parentheses. So here it is. But we had one of the homework assignments was like that. So it's do. What am I doing? I'm doing def macro while, and we need a test and body. Okay, so we have do, and there's no initialization form, and we have to put a back quote here. There's no initialization form. The test is not comma test, and then we want and that sign body. I think that's what we want. Let's see if it likes that. Oh, haha, yes, here's the problem. While actually already is a predefined function, so we're just going to have to give this a different name. Oh, that's much better. Okay, so now we do while, we have to set q I to 0, and then we do while, and what do we need? The test is greater than I10, and the body is print I and inc F I2, increase I by 2. So let's see if that works. Well, it objected to something.
I think you want less than.
While greater than, yeah, right, the test is this is what we're tried less than, and I falsely rejected it. Yeah, it's a shift. Thank you very much. Okay, there we go. So it prints I when it's 0, 2, 4, 6, 8. Then I is 10, and I is no longer less than 10, so it didn't print it. So there we go. Now let's look at what the macro expand looks like. Whenever you have a macro, you can always macro expand it and see what's going on. What do we want? We want the less than here. And so, so the system's worked on this a bit because it converted the do. See, what it's done is that it's converted the do in a way that we didn't completely expect. So the do's disappeared from here, but that's okay because do is a system. Do a macro? I never can remember. This is how you tell whether something's a macro. Yeah, so do is a macro, so the macro expand has also expanded the do. So this doesn't, notice that if we did macro expand 1, I wonder if we'd get the thing that would look more like what we're thinking. No, this thing already does its in. Oh, I'm sorry, I'm doing the wrong one. It's supposed to be while 1. I probably used while the whole time, and I should have been using while 1. Let me just and let's try that with macro expand 1. Macro expand 1 is just supposed to do 1 macro expansion. Yeah, finally. When I did this one up here, by the way, I was doing the wrong. This should have been while 1. Hopefully, we'll do the same thing. See, there already is a macro while. We're anyway, here's the macro expand. Why did my while 1 work? Try this one again. Doesn't work in either direction. Oh, that's curious. I wonder why it doesn't. Well, we'll look at that next time. I don't want to. Should work, and so anyway, so here's a macro argument with a list. Sorry, macro argument list. You can use and key and optional. You can use and rest, and often you do these things, and the macro argument list has within it a second list. And you see this, for example, with open file. Here we're defining a macro called with resource string. And so the argument list has within it a second list, which is a couple of arguments, and then the body goes outside that second list. And why is that necessary? The thing is that you can call this with just one argument, resource string, and then a body, or you can call it with an argument and a keyword argument and then a body. So if you didn't have this inner list here, how would it know the difference between resource string, with resource string called with one argument and then a body, and resource string called with an argument and a keyword? It would have to look at the second value in the argument list and see whether it was a keyword. However, keywords are perfectly good things to appear in a body. They're sort of bizarre. There's no reason to have them there, but there's nothing illegal about them. So in order, when you have a variable number of arguments that appear at the beginning before the body, usually wrap those in an interior string so the system can tell when, how many of this variable number of arguments you're passing, and that's what we've done here. And so here's what the body looks like. And, we're letting the variable here, that's the comma, changes this to the name of the variable passed. We're calling something called allocate resource string, which of course doesn't exist, but presumably you defined it, and here's a body, and then we freeze the resource string. That's the what we're trying to do there. You can put this is just making the point that a macro, it's not just a back-coded list. You can put logic in it, which will, if symbol is, if place is a symbol, then you use this back-quoted list. Otherwise, you use this back-quoted list. So all the examples before here have just been, most of the macro body has just been a back-quoted list, but you can put lots more logic in it if you want. Now, when you're using a macro, you have to remember that a macro is not a function. And therefore, certain things you can do with functions, like passing them as arguments to funCall or apply, can't be used with macros. And if you redefine a function, generally all the callers of the function immediately see that redefinition. But if you redefine a macro, the compiled callers of the macro have to be recompiled, because they have compiled the calls of the macro out, and they just expanded the code into the transformed code, and there you are. There's nothing, they have no memory of the fact that it was originally a macro call. So anything that uses a macro which has been compiled has to be recompiled. And then there are two problems. One's called the multiple evaluation problem, and the other is called the variable capture problem, and we're going to go into those in detail. Here is just pointing out you cannot call apply and give it the argument, first argument, the name of the operator being when. When is a predefined macro within Allegro Common Lisp, and this is just going to fail. You'll get an error. Apply will tell you its operator argument cannot be a macro. Now, here's the problem with evaluating more than once. And so there is already a macro within Common Lisp called OR, and it has the contract that it will go through its argument list, evaluating each element until it finds one of them that evaluates to a true value, in which case it will stop and return that true value, whatever it is. And so there are two elements of the contract of OR. One of them is that it will stop after it reaches a true value, and the remaining arguments will not be evaluated. And the second thing, which you may not think of, but in fact is one of its promises, is that each argument is only evaluated once. And so suppose that you said, all right, I'm going to define my own macro called OR1. It's just going to work on two arguments, but that's fine. And so here it is. If I'm going to evaluate the first argument, if that returns true, then I'm going to evaluate it and return its value. And if it returns nil, then I'm going to evaluate the second argument. Now, this fulfills half of the contract of OR, in that it evaluates the first argument and it doesn't evaluate the second argument unless the first argument returns nil. Remember, the OR promises to stop evaluation when it gets a non-nil value. But it violates the second piece of the contract because the first argument is evaluated twice. So, well, I hear you say, who cares? You evaluate it twice. Well, suppose that there is some side effect to the evaluation of the first argument. And an example of that is where you're calling the function print. It actually prints something. So if you call this OR1, print 2, it's actually going to print 1 twice and then return the value 1. Because it transforms into if print 1, there's the first, it evaluates that, and then that returns the value 1, which is true, and so it evaluates it again. So this is different if we called OR print 1, print 2. It would only evaluate the print 1 twice, and print would only be, 1 would only be printed out once. I think I said that right. If we called this with OR, print 1 would only be evaluated once, and 1 would only be printed once. So the simple way to avoid multiple evaluation is to capture the value of the first argument in a local variable and then do your testing with it. Now, we've only evaluated A once. This is now temp has the value of A, and we can evaluate temp as many times as we want because simply taking the value of a symbol of a variable has no side effects. You can look at it as many times as you want. Now, I have to warn you that although this solves one problem, it suffers from what is called the variable capture problem, which is a little bit more subtle, and we're going to go into next. So, but this does seem to solve, and it in fact does solve the multiple evaluation problem. This definition, or 2, does not evaluate its first argument twice under any circumstances. But, so here's the variable capture problem. So here's or 2, and we do all this temp stuff. Now, here we have a let x be nil, and let the local variable temp be 7. And then we do or 2 x temp. Now, x is nil and temp is 7, so this should return 7. But it doesn't. Why not? Well, here is what the macro expansion is. We let x be nil, temp 7, that's this bit here. And then we go into, here is the expanded macro. And then we let temp be x. That means x is nil, so we're letting temp be x. This overwrites this binding here. So now temp is bound to nil, and it says, well, what's the value of temp? It's nil. So we don't here, and then here's the temp appears again. So this is called the variable capture problem, and it doesn't, it not only, well, I mean, it doesn't have the effect of getting 2 side effects from double evaluation. It has a slightly different effect. You get a completely wrong answer, and that's not good. You never want to get a wrong answer. So there is a function within Lisp called gensim, and gensim will return a new symbol which is guaranteed not to already exist. And so you can create one of these symbols, and then it can't possibly be captured by any of the code above it because the symbol didn't exist prior to the call to gensim. So nothing prior to it, none of that let form, can cause a variable capture problem. The cost is slight because you are creating a new symbol, and that that has certain resource issues, but they're probably not significant unless you're calling this a zillion times. So here we have our third try at an OR macro with 2 arguments. We let the local variable symbol be a newly created symbol called by gensim, and then we let this newly created symbol get the value A, the value of A, not the symbol A, but the value of the symbol A, and then we test it. If it's true, we return that value. Otherwise, we evaluate B. And this one genuinely is an error-free implementation of the 2-argument OR. And here is what the macro expansion looks like. These generated symbols, if you did this, you'd see a different number there. These generated symbols are of the form no package, which is what this hash colon means, and then the letter G, and then a number. And it's gone through and looked at all the other ones and made sure that number is unique. You can often take a function and turn it into a macro. The advantage is when you have code that calls it, and you compile that code, the macro is simply transformed into the expansion code, and you have saved yourself a function call. However, you cannot do this with recursive functions. The macro expansion of a recursive function will often, the process will often go into an infinite loop. So here we have the function second takes the cadatter, or the second of a list X. we could change it into a macro, just like that. And then whenever we called, well, if you did this, again, it would whinge about the fact that second's already defined, but, if you called this my second, that would work. Here's the function sum, where we add a bunch of numbers, and we could change it into a macro. Again, what you're saving in your application is function calls, and that's desirable when something is being called in a loop and there are a very, very large number of calls to it. One place that you use macro is if you are doing the same kind of thing over and over again. Here again is our with resource string macro. You're, constantly getting a resource string, making use of it, doing something with it, and then freeing it. The example that's predefined in Common Lisp, which is with open file, we do that all the time. You're always opening a file, doing something, and then closing a file. And so the with open file macro simply provides all the wrapping code necessary to do that, the opening of the file, the closing of the file, and so on. Since you're doing that again and again, always exactly the same way, you open the file, you do something, you close the file, you having a macro defined to do that is very efficient. So this is one case where defining a macro is very useful. Now, you have to use a macro where you need to control the evaluation. Where you have, so when you call a function in those OR macros we had, what do we mean control evaluation? When you call the macro OR, remember that it will only evaluate arguments until it gets a non-nil one, and then it won't evaluate the remaining arguments. If you had a function, it would always evaluate all the arguments, first thing, before it did anything else. So you were already breaking the contract of OR, which promises not to evaluate after it's found the non-nil value. So that's what's meant by control evaluation. So if you want to do something where you've got local binding, if you want to do something with conditional evaluation, which is what and, or, if does, if you want to do looping, and if you want simplification without a function call, so that your code is more readable, and setf of car can be replaced with replaca, but this might be a little bit more readable. All of those things are times when you might define a macro. This particular last one is where you are really writing your own programming language and having it transform itself into Lisp. And now most of us don't sit down and write our own programming languages, but in some cases that's what you want to do, and you can do that. And then here, there are already a bunch of iteration and binding excuse me, and conditional evaluation forms that are predefined, but if you need one that's specialized to your purposes, you would use a macro and presumably the existing pieces and make something up out of that. You can also use macros, as I said. You can do computation at compile time. You can expand in place and avoid function calls. And you can save typing and code duplication. And in that case, it often clarifies the code. When you have a call to with open file, which is, as I say, one of the most useful macros, when you're reading code, you see a with open file, you know exactly what it's doing. If you had a let form where the first binding was to some variable which called open and the second binding was, so-and-so, you might be reading that for a bit before you discovered, oh, this guy's just opening a file, doing some stuff, and closing the file. With the with open file, you see a with open file form, you know exactly what's going on. Can't use macros if you want to use fun call or apply. The macro definitions are often harder to read. There are all these back quotes and commas and @ signs, and sometimes you're looking through them and it's just hard to follow. All the macros we've been doing are quite simple, but trust me, there are some that are incredibly difficult and incredibly hard to figure out what's really going on. Much more so than functions, because functions are often clearer because they don't have these commas and backquotes and @ signs and so on. Even more important when you're developing code is that macro definitions are harder to debug, because when you've compiled a macro definition, or even when you're running it interpreted, by the time that it's actually evaluating the code, the macro definition itself has disappeared, and it has been replaced with the macro expansion. So when you're looking at a backtrace produced by the debugger, you don't necessarily see anything there that resembles what you thought you were calling. And it is possible to have macros that expand recursively into other macros, but usually you can't do a recursive algorithm with a macro. And from my point of view, don't even try. Here, I've already said this, when you change the definition of the macro, you've got to recompile all the callers of the macro, or it won't see the changed definition. There are tools within Lisp. The def system tool allows you to set up dependencies of one file on another, and in what's called a file, a system. And so you can say, compile the system, and it will make sure that it compiles files in the right order. Also, another thing, if you have a macro and let's say we have a macro called foo, and we've already defined and compiled a function called bar, which calls foo. And we did that before we defined foo as a macro. Then the compilation of bar is going to assume that foo actually names a function. Because what else can it do? It's got to assume something. It's not an error to compile a function which calls other operators which have not been defined. But since they haven't been defined, the system can't know whether they're functions or macros or what, and so it just assumes they're a function. And let me just show you what I mean here, because this is a little bit easier to see this with. So let's share that. So get a new prompt here. So we define bar of x, and it calls foo of x. Okay? Now we compile bar. And notice that it warned me. It said, well, I was compiling this, and you made a call to something called foo, and I don't know what it is. I haven't seen the definition. Now we do a def macro of foo. Again, we take the and actually, there's no reason that we just can't do. Yeah, it's pretty much like that. So foo 2, 4, fine. So now we call bar of 2, and we would expect to get 4 because we just pass it to foo, pass the argument to foo. But instead, we get an error that says attempt to call foo, which is defined as a macro. And what it means is attempt to call foo as if it were a function, which is defined as a macro. So in order to fix this, actually, we've got to uncompile bar, and the easiest way to do that is just to put in the definition again, and then compile it again. What did I do? Ooh, isn't that clever? Let's redefine the macro. And That time it worked. So what was the problem there? It was expanding foo, and it said, okay, I expanded foo, and remember it just got expanded to plus XX. And so it said, wait a minute, X, I know plus, and X is a symbol, it's not a number. And so this is why when you're defining the macro, what we're doing is we want the macro to transform into a list that we have specified, and that's not what we are telling it to do up there. So now, let's call bar of 2, and it should work fine. We get 4. Okay, that's on redefining macro. Yeah, use macro expand on already defined macros within Lisp and see how macros are done. So here's some more macro stuff. Can't call it with apply. I'm going to go through this pretty quickly. Yeah, don't do recursion. So here we have def macro n star, where n is a list. And if n equals 0, then we take the car. Otherwise, we take n star of 1 minus n. When you macro expand this, it will macro expand forever because it just keeps macro expanding this thing. And n doesn't have a value, so it's just always going minus, n minus 1 minus n, just keeps wrapping around. And so my recommendation is, here is a macro with valid recursion. This is actually a variety of OR. And the point is that we're allowed any number of arguments here. And so we're slowly crittering down the list here. But each time we're getting a smaller and smaller list because, why does this work? It knows the list of arguments going in. In this case, it doesn't know the value of n going in. It just knows the value of n is the value of x. But here, it knows how many arguments you're calling OR star with. And therefore, it is taking, remember, it's macro expanding this form right here, and it's going through and slowly taking the cdr and then the cdr, and it knows when it gets nil because it knows when it runs out of arguments. So here's something where you can do a valid macro recursion. Spent my whole life programming Lisp, 20 years and more, never written a single recursive macro, so often you don't need to do that. Here's the multiple evaluation problem again, and we're just, I've already explained how to avoid that. Another important thing, this is a slightly more subtle problem, is the order of evaluation. Within Lisp, you are guaranteed to evaluate things, calls to operators, left to right. And in this case, it's evaluating things, the right hand, the second argument first, and then the first argument. And the point that you have to remember is that forms are valid arguments to operators, and they may have side effects. So here, both these forms are valid arguments, and they're each one is setting the value of the variable x. And so if you just called AND, that is the already defined Common Lisp function on set q x of 2, set q x of 3, it would evaluate set q x of 2 first, and it would return the value 2. That's non-nil, so then it would evaluate set q x of 3 and return the value 3, and that's non-nil, but that's the last form, so it would return 3. And would do that, as does and star. However, if you call this with and, you would expect the value of x at the end to be 3 because it evaluated this argument first and then this argument. And the result of this is to set the value of x to 3. But and star actually, after it finishes, has set x to be 2. I should point out that this also violates the contract of AND, so this isn't a proper implication of AND, because AND promises not to evaluate B if A returns nil. And this one evaluates B first thing. But this is a kind of subtle problem, but you may run into it. And the thing is that if what you're thinking in calling operators is, okay, the arguments are going to be numbers or symbols, which we're going to take the value of, and you forget that the arguments can be forms that will have side effects, then you will run into these problems. You always have to think, what if this is called with a form that will have a side effect? Will that side effect occur at the wrong time or occur more than once? Here's another rather subtle problem with macros where you are destroying the argument list. And so here we have the sum plus. It takes a bunch of arguments, and it builds up a so what the result of this macro expansion is going to be a list where the first element is plus, and the remaining element is nconc args and list 1. What nconc does is it takes its list, it has a whole bunch of list arguments, and it bundles them all together just like append does, but it affects its argument lists. And while if we used append here, that would be okay because it makes a copy of. So this should work like plus with any number of arguments. Now we define foo to be sum plus of 2, 3, and the point is the argument list here, that's bundled up into a list, the list containing 2 and 3, and the point is nconc is modifying that list. So the first call returns 6, which is right. 2 plus 3 is 5 plus 1. And the second call returns 7 because it messed up this argument list, which is defined basically as a constant within this function, is being modified. And, so foo keeps returning incorrect values when we think it should always return 6. This is because the macro, as it says, is destructively modifying the source code of the caller. However, if you compiled this, then you wouldn't see this effect. But basically, the rule is don't depend on compilation solving your problems. Don't destroy argument lists. Fairly subtle problem, but you might run into it if you use destructive functions. And the two that you might run into are sort and delete. Those are the destructive functions everybody uses without necessarily remembering they're destructive. The result is that you should make copies of the list. So this would work if there were nconc copy list args list 1. Variable capture we've already gone through and gave an example. Global variable capture is similar. We have a global variable called width, and here we have a macro called notice width, which sets the value of the global variable to the argument. And here we have a function, draw rectangle, which has width as a argument. And so it calls notice width on height, and it calls notice height, which we haven't defined, but imagine it's the same thing, on height. And the thing is that because we have set this as an argument, this won't actually affect the global variable width. Now, the solution to that, I told you, no, I guess I haven't told you in this class. I told the people who took the elementary class in the past weeks that whenever you define a global variable, you always name it with a symbol bounded by stars. So if you called this star width star, and here star width star, then when you're just writing up an argument list for a function, you don't give it arguments that have stars on either side unless that's actually your intention, unless you're actually wanting to use the global variable. And so that convention, it's not a requirement. This is all perfectly legal code. If it doesn't do what you, even though it doesn't do what you want, it's not illegal. But that convention of naming global variables with stars around them is one that is, works out. And so you would avoid it in this case, and that's what this slide says. Here's variable capture again. Here's another example of variable capture where you're using bindings, and just follow this example through, and you instead of doing a whole bunch of bindings here, you do one set of bindings, and then you do a different set of bindings, and you'll get the right result. More variable capture. I don't want to go through these examples because we've already seen them, and you can look at the slides later if you need to understand them more. Just some more discussion of setf. Remember, it works on a place, so if you have something that accesses, say, accesses the first element of the list, you can apply setf to it and modify the first element of the list. Whole bunch of things are predefined with setf, first, second, all the list accessor functions, the array accessor functions, many of the sequence accessor functions, slot value, et cetera, et cetera. And you can define setf methods. We discussed some of this before. There's also a defsetf macro, which is takes sort of two argument lists there. The thing that is here's the function being set, here's its argument, here's the new value, and so this is the argument list, here's the new value, and this is what a defsetf would look like. Now, we're just going to quickly run through this last topic from the first time, which is closures. Then we'll get on to CLOS. A closure is kind of a thing that's unique to Lisp. It's an executable function, and it's an object with state. So it's a kind of function with memory. Basically, you get a closure by having a variable whose value is a function object. So here, we're setting the value of the variable closure to the result of this let form here. And in this let form, we're binding the local variable list to this list, and then we define the anonymous function lambda, which pops the list. And so now, the value of closure is this function object. If we fun call it, it is remembering this list that it was provided, and it pops it one at a time, and eventually we'll start getting nils if we keep fun calling down here. So the lambda created an anonymous function. It observes the rules of lexical scoping. The function can continue to reference the list even after returning from the let. That's the point. The function makes a snapshot of the variable. Here is a example where closure 1 and closure 2 are both operating on the same list, and so we get 2, the value of this is a closure, the value of this is a closure, and notice they're both operating on the same list. So when we fun call closure 1, it pops off the 1, and now we fun call closure 2, it pops off the 2, because they're both seeing the same list here, not different lists. Both referred to the same variable. Closures happen implicitly. This is where you mostly use them whenever a function refers to something in the lexical environment. And so here, I pointed this out before in the homework. Here we have a mapping function, and it has one of the arguments, num, appears in its definition. And so this mapping function creates a closure, and it knows about the value of that argument. The creating closure allocates memory can be a source of garbage, but you can allocate them on the stack by, here's the labels function. The labels special form. Remember, that allows you to define local functions we're defining the local function adder. Here's its definition, takes argument x, adds x to this value num, therefore you get a closure. And you can put in a declaration saying when you compile this, keep it on the stack, give it dynamic extent. And then, so whenever you call add to list, it will create one of these closures, but it will allocate it on the stack and it won't use up memory, is the idea. So here we are, we're defining a function add to list, and then we're defining a function make adder, which has a closure in it. Both of these have closures in it, and here are, so yes, both of them, and therefore both of them return closures. That's the point, and so we're setting these variables, and their values become closures, and then we can call them. And let me just run through this. You see here again, we are defining a local variable counter, and then we're defining a function reset that refers to counter in the scope of this let statement, and a function stamp that refers to counter. This one sets it to 0. This one increments it. So now, when we look at the values returned, stamp, stamp, reset, stamp. So sets to 1, 2, and then back to 0, and then back to 1. Here's another example where it is going through a list, and it's figuring out which elements of the list are odd and which ones are even. And again, it's using a closure. So the map car takes a function as its first argument. This function, my complement, returns a function object. That's the point. And it will return a function object. We could do odd p, we could do even p, whatever. And I'm just going to leave you with this example, which you can look at. Guy Steele, who was one of the early Lisp pioneers, showed a way to use closures in an elementary form of object-oriented programming. And you should look at this example. And that brings us right to today's topic, which we're going to go through. We'll probably not finish all these slides today, but we will finish everything up by the end of the next session. We're going to talk about the Common Lisp Object System, or CLOS. And when you were using the object system, here are sort of the 10 things that you do. You start defining classes. A class is defined with a defining macro called def class. Here we're defining the class position. Probably illegal because there's already a Common Lisp symbol called position, but sometimes easier on these slides to give meaningful names. And if you ever run into a problem, just modify the name a bit with putting a 1 on the end or something. And when you define a class, it has slots. This has slot X and slot Y, and you can give certain information about the slots. We're going to go into these things in more detail. Once you have created a class, you can create instances of that class, and you do that with the function called makeInstance. So here we are creating an instance of the position class, and it has an X slot with an accessor X position, and we didn't give it a value, so it got a default value 0. Here we have makeInstance position. We're giving X and Y values of 10. The slot argument is :X, and I think probably we defined that. Yes, the init arg :X. That's the argument. Keyword argument you pass to makeInstance. The accessor is X position. The init form is the initial value. If a value isn't specified, is 0. You can define subclasses. Here we're defining the aircraft subclass of position, and it has additional slots called speed and flight number. And now we can make an instance of aircraft with a position, a speed, and a flight number. once you have defined classes, you have instances on them, you can define methods. A method is like a function, but one or more arguments, and they must be the required arguments, are specialized so that this particular method will only run when the argument, the first argument, the only argument, is an instance of the class aircraft. And so the name will create flight number, and then access flight and access the flight number. The draw will take an aircraft and some stream to draw to, and it will draw the position of the aircraft on that stream. Presumably, the stream is some kind of graph or text graphics window. Method combination. Here we have a new class called aircraft with icon, and it is just a subclass of aircraft. Def class, the first argument is the name of the class. The second argument is the list of superclasses, and the third argument are the list of slots. And there are no additional slots here. There's only one superclass aircraft. It inherits all the slots from aircraft. Then we can define what's called an after method. So remember draw icon. Did we define draw icon? No, we just defined draw. Oh yes, this is our version of draw. We've already defined the draw method on aircraft. This is the draw method and after method specialized on aircraft with icon. And after drawing the name, draw the icon. And so we have some function draw icon, and it draws the plain icon at the position as well as the name. In other words, this will run the draw method on aircraft because aircraft with icon is an aircraft. It's a subclass of aircraft, and therefore it is an aircraft, just in the same way that if you're an American citizen who lives in New York, you're an American and you're a New Yorker. All New Yorkers, assuming they're all citizens of New York, are Americans. You initialize instances. So here we have, that is, when you create an instance of something with make instance, a predefined generic function called initialize instance is called by the system, and you are allowed to add after methods to initialize instance. You never redefine the main method for initialize instance, but you can produce an after method, and this after method pushes each aircraft that is created by initialize instance onto some variable list, which is the value of a variable of all the aircraft that have been created. You can use slot value to access the values of slots of an instance of a class. Now, here we have set position as a method. It is defined when the first argument is a position object. Very early in number 2, I think, we define, well, number 1, we define the class position, so there are position objects, and it takes 2 additional arguments, x and y. And it sets the x slot of the position to x and the y slot of the position to y, and then it returns t. And we also have get position, takes a position object, and it returns the as multiple values. That's what values here, the x and values of the x and y slots. Now, we have a hierarchy of classes. We define the class position. We define the class aircraft, which is a subclass of position. We define the class aircraft with icon, which is a subclass of icon. So get position and set position work for aircraft, positions, and aircraft with icons, because all of those things are positions. The aircraft are also aircraft and have additional properties, but they, because it's a subclass of position, they're positions. Now, you can always access the slot with slot value, but You can also access slots with accessor methods that are defined in the def class. Way back in the first slide, we defined a def class. We defined a slot X, and we said it had accessor position -X. You generally prefer to use accessor methods such as X position and Y position over slot value. But if the accessor function has lots of after, before, or round methods, slot value is faster. And you may have defined an after method which you want to avoid, in which case you can use slot value. The reason to prefer the accessor method is that if you redefine the class and give the slots different names, that you have to go find the slot value references and fix them, but the accessor method you can simply redefine, and the redefinition will be seen. There are setf methods that you can define. So here, the name of the method is setfxposition, and it's an after method, and it takes, here are the arguments. The third thing is the argument list, a new value, and then an aircraft object, and it redraws the display and causes a redisplay when the position changes. The thing is that there already is a method of setfxposition, which is predefined when you define the class and the accessor xposition. You are defining an after method, which will run after somebody has set the xposition to be something else. And assuming that we had defined these functions, redraw display, and we had some kind of graphic stream that could do that on, this after method would be called whenever the position was changed by a call like this. Multiple dispatch. So here it's just, the point is, here are a whole bunch of different methods, phase methods. They all have the same name, but they take their first or second argument are of different classes. So it's defined for a position, and when stream is a file stream, it's defined for a position. When stream is a database, it's defined for an aircraft. When stream is a file stream, it's defined for an aircraft when it's a database. Now, every aircraft is a position, but when you run a method, it looks at the class of the argument and takes the most specific class for which there is a method defined. So if you call save on an aircraft, it will take this method or this method, depending on what the second argument is, and it won't run the position methods. Now, these look the same, but they could have different code here, and that's why it's important. The example that it's giving here is that we are dispatching on not one but two arguments. So it depends both on the class of the first argument and the class of the second argument. And as many required arguments as you have, you can dispatch on every one of them. Multiple inheritance says you can define a class that has a number of direct superclasses. And so this new class inherits from all three of these. So it is, as it says here, in most ways, the union of the structure and behavior of the components. It gets a little bit confusing when these different classes have slots with the same names that behave differently, and then the question is, which slot does it actually inherit from, and we'll see that later. Okay, so I'm just going to push on through these CLOS examples. Just a little bit of history. There's been various object systems within Lisp, and CLOS was included in the ANSI Common Lisp. You define classes of objects using def class. You create or make objects, and that's called instantiation. And you do that with a call to make instance or a call to a creator function which itself calls makeInstance. Slots are also called instance variables, and when you call makeInstance, you can set the values of slots using the instance arguments. Their older object-oriented systems talk about messages, but in Lisp, these are called generic functions and methods. And well, generic functions are messages, and the methods are specific to various classes. So here we have the class, for example, rectangle, and it's got 4 slots: left, bottom, width, and length. And here are 2 instances over here in blue, and they have some same and some different arguments for the 4 slots. Even if all the values were the same, they would still be different instances, different objects. The instances of a class have slots. The slots have names and values. And there are 2 kinds of slots, one called a local slot, and that applies to the instance alone. And the other is called a shared slot, and that applies to all the instances. And so if you have a local slot and you modify it for a particular instance, it doesn't affect any of the other instances. If you have a shared slot and you modify a value with one instance, you modify the value for all instances. So here we're discussing class inheritance, and there are built-in classes in Lisp. I hope you can see this, a little bit small. At the very top, the superclass of everything is the class T. Right under that is the class called standard object. And below that, we start getting classes that we're defining ourselves. If you do a definition of a class with def class and you don't specify any superclasses, then it automatically gets standard object as its superclass, which has superclass T. So here's rectangle down here, which we've defined. And let's say we've defined 2 subclasses, labeled rectangle and filled rectangle, of rectangle. So here's just some terminology. Rectangle is a direct superclass of labeled rectangle, which is a direct subclass of rectangle. Labeled rectangle is a subclass of standard object and a subclass of T. Standard object is a superclass of labeled rectangle, and T is a superclass of all classes. So direct means you're moving one level up or down, and then if you don't use the word direct, you can go as many levels up for a superclass or as many levels down for a subclass. CLOS, again, supports multiple inheritance, and so suppose we have a class called display object. It might have a subclass called labeled object. Here's our, maybe it has another subclass called rectangle, and then labeled rectangle has both of these as superclasses. Now, the labeled object has slots label and font. Rectangle has slots left, bottom, width, and height. Labeled rectangle gets all 6 of these slots. The class inherits a union of the slot descriptions. In ordinary function, and if you were going to dispatch code on the value of the argument, and you were writing an ordinary function, you'd have to write some kind of conditional which would study the argument and figure out how to do the dispatching. So here we have a function called area. It takes a shape, and then we say, okay, is shape a circle? Well, in that case, we figure out the radius, and we take pi r squared. Or it's a rectangle, in which case we figure out the length of the 2 sides and we multiply them together. Or it's a triangle, and we do whatever you do, 1/2 base times height. So this is what a normal function, which is doing different things for different arguments, would do. A generic function, the dispatching is done outside the function call. So here we have area. We have a generic function called area, takes an argument shape. And here we define 3 methods. When shape is a circle, we do this. When shape is a rectangle, we do that. When shape is a triangle, we do yet another thing. So here's an ordinary Lisp function. The dispatch code and the specific code is all within the function definition. In a generic function, the system takes care of the dispatching, and the user code is just what to do for the various classes. So that's the difference between a generic function, which dispatches on one or more of its arguments, and an ordinary function, which simply takes the arguments and then the user code has to figure out what to do. So here, in order to fit this in, we're getting really tiny, and I hope you can see that. This is def method draw. These are all def method draw, and we have shape, rectangle, and then stream, PostScript stream or window stream. And here we're dispatching both on the first argument shape and on the second argument stream. And in this case, shape is a rectangle, and we do two different things. Shape is a circle, and we do two different things. Now, therefore, methods, because of multiple dispatch, you don't talk about methods belonging to classes. They belong to a combination of one or more classes depending on how many arguments they dispatch on. And if you're familiar with other systems like message passing object-oriented systems, it implements class as messages are associated, but we don't do that. So if you're familiar with that, you probably know what that's talking about. Methods are associated, however, with the generic function. There's always either a explicitly defined or an implicitly defined generic function associated with a method. Each class in the list of superclasses can contribute a component to the effective method. So when you are calling a generic function on an object, the question is, which of the various methods that have been defined with the name of a generic function, which one of them is going to actually be called? And the name for that is the effective method. And so suppose that you have, a class foo, and it has direct superclasses bar and baz. If you have, and you're looking at the, save method, there's a save method defined for bar and a save method defined for baz, and not one specifically defined for foo, then it's a question which one is going to run. And there also with methods, you have what's called the primary method, and you have before methods and after methods. Before methods run before the primary method and typically do error checking and preparation. After methods run after the primary method and do cleanup. And we're going to see some examples of this. So the way you determine which method runs is by using the class precedence list. The class precedence list is a list of superclasses. So you look at a class, and then you can list all of its superclasses, going from its direct, one or more direct superclasses, all the way up to T, and you can arrange all of these classes in an ordered list, which is called the class precedence list. For single inheritance, obviously, you just, in other words, each class only has one superclass, a direct superclass. Then you just sort of go up the direct superclasses until you reach the one that has a method defined on it, and that's the method you run. So for single inheritance, the ordering is obvious. You just find the most specific method which is defined, going up the direct superclasses. But with multiple inheritance, the class precedent list is computed according to the local ordering. When two classes order completing straights, when two classes in the class precedence list have competing methods, you pick the one that is associated with the class that's earlier in the class precedence list. So here we have def class. Here's how you define a class. We'll get back to this class precedence thing in a minute and give some examples. But let's go back to defining a class. Here we call the defining macro def class. The first argument is the symbol, which is the name of the class we're defining. Then there is a list of superclasses, and this will always include, even if you don't put them in, standard object and T. Then there are a list of slot definitions, and each slot definition can be just a symbol, in which case that's the slot defined, or it can be a list with additional information. And the typical information is the init arg, that is the name of the argument keyword argument you would give to make instance when you're creating an instance of this class. Another typical thing you specify for a slot is the accessor, which is the name of the function which will access the slot value or set the slot value when used with setf. So here we have, again, our class, well, this is point rather than position, but we have an x and y. They both have an init arg, and they both have an accessor called point x and point y. So here are all the choices. You can have the init form, which gives a default value. We didn't have one here, so these things start out with probably no value. They have an init arg, which is the argument you can use in the call to make instance. They have a reader, which is a function which can only access the value but can't set it. They have a writer, which is a function which can only set the value but can't access it, used with setf. And then you have the more common accessor, which you use instead of a reader or writer, and it can both read and write. It can both access the value and set the value. Now, def class itself has some additional options which come after the definitions of the slots, and one of them is the documentation is a descriptive string of some kind. The second one are default init args, which are additional arguments that you can specify, but which aren't associated with slots. So let's see. Here we have defining the class circle. It's a subclass of point. And, I'm sorry, the default init args that are associated with slots that it's inheriting from its superclass. Point, remember, has slots x and y, and so this is saying that circle has an additional slot called radius, which has the default value init form 5, has an init arg :radius, has an accessor called radius, and it's got documentation, a round thing, just a string, and then it also has default init args, which are giving init args for the slots defined by the point class as being 0, 0. Now, when you are defining an interface, you can call def generic, which is a defining macro that defines the format of a generic function. Generic functions defined with def generic are the def generic form itself does not contain any body. It doesn't tell you anything to do. All it's doing is defining the structure of methods that will be defined. And so def generic, calls to def generic are optional. When you call def method, if there isn't already a def generic form defined, it will sort of create one implicitly based on the structure of the def method. So see, here we have def generic draw apart. It takes 2 arguments. That's the important thing, 2 arguments. Notice that we're not specializing on those. Def generic won't specialize. It's just saying the draw apart generic function is going to take 2 required arguments. And it can be given a documentation string, and it can be given a few more options, which we will discuss later. So let's see. Now, when you want to write actual methods, then you specialize on the required arguments. And in this method, the first argument is specialized. It says when the part is an instance of the class circle, then you're going to call this method. The second the second argument is not specialized. It's called an ordinary parameter, and you could view it as being specialized on the class T, because that is the superclass of everything. There are one or two subtle differences between leaving it unspecialized as an ordinary parameter or specializing it on the class T, but mostly they wouldn't concern you. But typically you don't specialize things on class T. You just leave them as ordinary parameters. Here we actually have a body. We're doing something. And here we're drawing circle on the stream and, assuming that, well, actually that function does exist within Common Graphics. So assuming that you had stream being a graphics window, it would actually draw the circle. Now, whenever you create an object, you create it with make instance, and here is an example of, assuming we had a class called square, which we haven't actually defined, but pretend we did. Make instance of square, and it's giving its x and y, assuming it has slots called x and y, values 0 and 0. And in any call to make instance where there are init args defined, you can specify their initial values. Once you have an instance of an object, and here I should have defined the class square. We used to, but we simplified the slide slightly, and we don't bother with that anymore. Once you've defined once you have an instance of a particular class, then you can apply slot value to access the value of a particular slot. Slot value always works as long as you know the name of the slot, and slot value always works with setf as long as you know the name of the slot. And there is a macro defined called with slots, and it takes as its argument list here as the argument list, the first argument is a list of slot names, in this case X, and then the class, the object, my square, an instance of the class square, and then a body, and the body will, the value X will be the value of the X slot of the my square instance. You can do things like setq and print, and it will convert these things into the correct form. This is called syntactic sugar because the with slots is just an easy way of doing something which you would normally do. If you macro expanded this, it would macro expand out to something like that. Finally we defined the class square with the initial arguments, with the slots x and y, and width, and the init forms, and the init args, and the accessors. And so here we're defining, creating an instance of my square. Actually, this slide's out of order. It should have been like 3 slides ago, because we've been looking at the instance my squared. Now, it is strongly recommended that you create for classes that you are going to create instances for, you create what's called a constructor function. And here we're defining the function make square. That's the typical name of a constructor function. And it's getting 3 arguments, x, y, and width. And then it calls make instance with the argument square as the name of the class, and then :x, the value of x, :y, the value of y, and :width, the value of width. The advantage of this is that you now have a functional interface for instance creation. You don't have to call make instance and then fiddle with a lot of arguments like the class name and so on. Instead, you just have a function called make square. It takes care of calling make instance, and it provides the arguments that are relevant. The thing is, make instance, it does no checking whatsoever. If you've supplied all the init args, you haven't supplied the init args, and it's somewhat tolerant on taking a whole bunch of arguments, and it doesn't do, it's just not a tremendously friendly function. And the idea is you're writing here a friendly function for creating instances of squares. Another advantage is that if you decide, all right, I'm going to redefine my class square, and it's going to have, it's going to have, instead of slots X and Y, it's going to have slots A and B. Well, then you just have to redefine your constructor function here with arguments A, B, and colon A here and colon Y, and anywhere else that you have called make square, it'll still continue working fine. But if you had calls to make instance with quote square and so on, you'd have to go find all of those, which is not the easiest thing to do in a big program, and modify them in order to use the slots A and B instead of the slots X and Y. So that's what it means down here. The class name is not advertised. You're not telling your users about the internal structure of what you're doing, because when you don't tell your users about the internal structure, it's always easier to change the internal structure. So here we have another class called rectangle, which is a subclass of square, and it has an additional slot called height. And it inherits the rest of its slots, width, X, and Y, from square. So now we have my rectangle, and we can specify the height init arg. And here we define a method called area. And when the object is a square, we multiply the width of, we get the width and we multiply it by itself, and so we square the width. And so the area of my square, if we go back and look at the instance we created, presumably it has a width of 15, and that's 15 squared is 225. But the area of my rectangle, let's see, do we define a my rectangle? Yeah, there we go. My rectangle is a width 10 and a height 12. And if we now apply area of my rectangle, we get 100, which is wrong. It just squared the width. But rectangles also have heights, and their area is, of course, height times width. So we have to define a method specific to rectangles, and we multiply the width by the height, and now we get the correct answer. And one thing you may notice is that the structure of your classes, we're having rectangles as a subclass of square. And if you kind of think about geometry, you might say, wait a minute, squares are a particular example of rectangles. It really should be the other way around. But the reason that we've made rectangle a subclass of square is that rectangle is the one with the additional slot. It needs a width and height slot, while square just needs a width slot. So the easiest way to define it as far as Common Lisp and CLOS is concerned is to have the superclass be square and the subclass be rectangle, because you want your subclass to be the one with the additional slots. Things get a little complicated otherwise. So the class structure need not mimic the kind of structure in the real world. The class structure is set up in order to facilitate programming within your application. It's not claiming to be a mirror of the real world. So anyway, area, you have to define a method specific to rectangles, because the method that's specific to squares won't work. There are a bunch of the typical accessor functions. You get the class of something. You can get the class name if you're given a class object. So class of returns a class object. Class name applied to that gives you the name, which is square. Type P of my square is a square. Type of my square is a square. My square is also a standard object, and it's also of class P, because type P will return true so long as the class specified here by name is either the class of this object or a superclass. There's a function called describe, which you may be familiar with, and it will tell you interesting things about any particular object. So slot value, we've talked about slot value rectangle width. You can get the width slot, you can get the height slot. Notice that if you try to get the height slot of my square, which is an instance of square, you get an error because there is no height slot for squares, only for rectangles, and my square is not a rectangle. You can set F the slot value, and that, of course, changes it. Slot bound P determines whether the slot has a value. Slot exists P determines whether an object has a slot of a particular name. Slot MAC unbound removes the value from the slot and causes slot bound P to return nil. When you're creating slots with def class, there's the accessor option, and it defines a function. It names a function for accessing the slot. Again, it's recommended that you use the accessor function instead of slot value. The advantage, you're not advertising the slot name. You're not telling your users about the internal structure of your application. Always a good idea because then you can change it without them worrying about it. The init form slot option just gives you the initial value in a slot if a specific value isn't supplied. The init arg just gives you a keyword which you use with make instance when you are creating the slot. And you can specify a value for creating an instance. You can specify a value for the slot in the call to make instance, like here we do with height. If you don't specify a value for the slot and there is an init form, it gets that value. If there is no init form, it's unbound. The allocation slot option, there are two kinds of allocation, are instance and class. And earlier we referred to these. The instance allocation, each is the local one, and each instance gets its own slot value. The class one is the shared one, and all instances have the same slot value. Excuse me. Here we're defining the class rectangle. It's a subclass of basic part, which I don't know if we've defined yet, but just imagine it's a class of shapes. And there's a whole bunch of stuff, but here we're defining, this is presumably other slots which we're not defining yet, or which we're not showing here. But one of the slots is called number of sides. It's got a reader called number of sides. And it's got an init form 3, and its allocation is class. That is, every instance of the class triangle will have a slot called number of sides, and they'll all have the value 3. Now, shared slots actually aren't much used, and you could easily live without them. And here we define a method for number of sides when part is a triangle, and we get 3. And therefore, if you apply this method to any triangle, you'll get 3, just as if you applied the number of sides accessor to any triangle, you would have got 3. So shared slots or class slots were kind of an idea which is, sort of interesting, but actually not all that useful because you can do things in a more natural way. Remember, when you change the value of a class slot for any instance, the change is seen by all the instances. And that's always a mildly dangerous thing to do from my point of view. That's why I'm not a big fan of class or shared slots. So methods associates behavior with objects. Here we have a class called point, which we've seen before. We can have a method distance, taking two arguments, both of which are points, and then we use Pythagoras' formula with the function Pythagorize, which takes the difference between the x values, difference of the y values, and then adds the sum of takes the square root of the sum of their squares. That's the Pythagorean distance between points. The method you get depends on all the arguments, as we've said. So here we have a def class dot, and it actually has a size argument, and the idea is that a point has no dimensions, but size actually has. You view it as, an actual filled circle centered at a point, and it's actually got a size, which is basically the radius of the circle. So here we have distance from point and to dot. And again, we do Pythagorize, and we subtract out the dot size. In other words, if we have a point and then we have a dot, which is one of these sort of filled circles, the distance is the distance between the point and the center of the filled circle less the radius of the filled circle. That's what dot size is. So now we have two methods on distances, one where it's a point, and one where it's a point and a dot. So if we call this with a point and a dot, we get this method is called. Otherwise, if we call it with 2 points, we get the previous method. Now, as I said, you can dispatch on T, which is the class of all objects, and these things are, here we're defining distance. Distance really is only defined, say, between points or between a point and a dot. And so here we have a def method for distance where from and to are both of class T, and then we signal an error, or where from and to are just simply unspecified, and we signal an error. These are, from the point of view of behavior, these things are identical, and they're nearly identical in all respects. And the point is here now that we can now call the method distance, and it will do something no matter what arguments you pass to it. Before, when we just had a method defined on point or point and dot, if you gave it, say, a square and a circle, it would signal an error, but the error would say there are no methods defined when the first argument is of class square and the second argument is of class circle. But there is so here we're actually controlling it so that we get to call the error. We get to decide what error we're going to call. So there's another way of dispatching, which is when the argument is EQL to a particular symbol. This is useful. We have a notion of an origin, and here the second argument is 2, and then we call distance on. We create a point with 0, 0, and just pass the second argument, which hopefully will be a point or a dot. And so now we can call distance from origin to this point, and that will be 5, which is 3 squared plus 4 squared. 25 square root of that is 5. So here, this is called dispatching. Here we just have the keyword origin, and we defined a method called an EQL method, where it would call this method when the first argument was EQL to origin and the second argument was anything at all. And here are some examples of this. Now we have a place, and we have a def method name is someplace. Then we have home is make instance of home, and office is, these are 2 offices. And now we define methods when the argument is EQL to this home instance of place. Then the name is my home. When it's equal to this office instance of place, it's my office. And so we just take any instance of place and apply the name to it. We get someplace. But when we apply it to office, we get my office. Notice these aren't symbols. They're actual objects, instances of the class place. Before and after methods. Before run before the primary method. After methods run after the primary method. You define whether it's before or after with the keyword before, or the keyword after that appears after the method name and before the argument list. The return value, if any, of before and after methods is ignored. The order of before and after methods. Now, it is going to run all the before methods defined on a class and all of its superclasses, and it will run all the before methods, the most specific before method first, and then all the way through to the least specific. So we have, position, which is a subclass of standard object and subclass of T. If you had a before method on T, a before method on standard object, and a before method on position, then it would run the one on position first, then the one on standard object, then the one on T, and it would run all three of them, which is different from the primary method. It only runs one primary method. The most specific primary method is then run, and then all the after methods with the most specific last. And so if there were three after methods, it would run the one on T first, then the one on standard object, then the one on position. The point of this is that you can define after methods that do some kind of general cleanup and then do some slightly more specific cleanup all the way down to the most specific cleanup. And you can depend on all of these methods running, and from the least specific to the most specific. Now, an around method is this is probably the last concept we're going to get through today. An around method is one that shadows all before, after, and primary methods. So when you have an around method, it is called, and if it does something, whatever it does, unless it explicitly tells you to start calling some more of the methods, as we will show, it can prevent any other methods from running. So an around method shadows everything. Its values, the value returned by the around method is the value the generic function returns, unlike after methods where the values are ignored. Only when you just have before and after methods, it's the value returned by the primary method, which is returned by the call to the generic function. But when you have an after method, it's the value returned by the after method, which is returned. When there are nested around methods, it always starts with the most specific. So if we have methods on position, standard object, and T, it runs the around method on position. Now, within the body of an around method, you can have a call to the operator call next method. And it will then look, and if there is a less specific around method, it will be called. If there are no less specific around methods, then it will call the most specific before method. If there are no before methods, call next method will call the primary method. So the way that an around method doesn't just shadow and prevent any of the methods, other methods from running, is by calling the operator call next method. And if you don't have a call next method in there, then none of the other methods will be run. Now, when you are in a primary method, suppose we have a method on position, a method on standard object, and a method on T. These are primary methods, not around, before, or after. Then only the primary, when you pass a position argument, only the primary method on position will run. It will run, and then it will return a value. If a call next method appears in the definition of a primary method, it will go to the next most specific method, the one on standard object, and it will run that. And then its value will be returned by this call to call next method, and then this primary method will continue running. But if, and you can do the call next method, you can pass additional arguments to it, as we've done here. Normally, call next method calls the next method with the arguments that were passed in, but you can call it with different arguments if you want. So here is a call next method example. So we have, here we're just using standard classes within Lisp. A is a list. Here we are defining a method where the first argument is a list and the second argument is anything. Then what it does is it prints out first argument of A is a list, this thing is a list, and it's you remember format, that's a line feed. And then we do a test. There's an operator called next method P that returns true if there is a next method, otherwise returns nil. So we test to see whether there's a next method. If there is, we call it. Now we define a method on B, which is a number, but A can be anything. And we say second argument is a number, and then we call the next method if there is one. So here we're calling foo on the list 1, 2, 3 and the symbol A. And it says first argument is a list. And then it calls the next method, but there isn't any next method. We have no method defined on a list and then a symbol, or on anything and then a symbol. We just have it defined that fits this case on lists and anything. And we've already run that method. If we call foo A3, A is the symbol, so we're calling the second method here. The second argument is a number, and so it prints out second argument is a number. And when we call foo with the first argument being a list and the second argument being a number, it says first argument is a list, second argument is a number. So I hear your question, why did it choose this one first, and then why did it choose the method on list first, and the method on the second argument being a number second? And the answer is that's the order in which the arguments appear in the generic function. And we will later see that you can tell it, well, process the arguments for this purpose in the opposite order, and we'll have an example of that. So that's all we have time for today. We're still a little bit behind in the slides, but I promise you next time we are going to catch up with all of these slides and finish all the slides from the next time. There are a fair number of slides next time, but most of them we go through pretty quickly because we're just showing you how to do things. The homework involves some of these CLOS things. They're about, 39 slides, 39 slides left. So go through the additional slides if you want. Let me just zip to the end here and just remind you of the email address and the email address for questions, training@franz.com, the homework and so on, www.franz.com/lab, and you have to put in the /lab. There's no link from the main web page to this because this is for class members only. Very good to see you all again. Thank you. We're going to have 10 seconds of silence so that the recording can know where to stop. And see you all next time. And I do encourage you to send in any questions you have. I've got several, and I encourage questions from everyone. Thank you very much.
Thanks, David. Have a good day.
Have a nice day.